As you know, cells are the basic unit of life. They form tissues, which form organs, all of which we need to survive. They can multiply indefinitely under the right conditions, can differentiate into any kind of cell the body needs, and will even commit suicide if the body needs it to. Organs from stem cells in a lab sounds really complex, doesn't it? Well, it is, but scientists have already made significant progress over the years. Let's learn more about this process from our very own Dr. Nishila Mehta.
Let's start off with learning what exactly a stem cell is. A stem cell is a cell that has the amazing potential to develop into many different cells in the body. When a stem cell divides, each new cell has the potential either to remain a stem cell or become another type of cell with a more specialized function, such as a brain cell, a heart cell, or a blood cell. Also, in many tissues, stem cells serve as a sort of internal repair system, dividing without limit to replenish other cells when wounded or damaged, as long as the person or animal is still alive. Next, in order to create artificial organs, scientists begin by creating a scaffold. A scaffold is a structure that can be either natural or artificial that maintains tissue contour. Scaffolds can be made from existing organs. One method is pumping chemicals into an organ that strip it of its lipids, DNA, proteins, sugars, and almost all of the other cellular material from the heart, leaving only a pale mesh of collagen and other structural proteins. This is called an extracellular matrix, which is the structure that once held the organ together. Artificial scaffolds, on the other hand, are often made of plastic and glass. The first step is to cover the scaffold in stem cells and cells from the donor. These stem cells must come from the patient. Antigens on the stem cell from one's body may cause a patient's body to reject the organ. This is why all stem cells must come from the patient themselves. Luckily, embryonic stem cells are not necessary for this process. Cells from bone marrow or skin can be used instead. Some scaffolds also release chemical signals to encourage cell specialization, and the material of the scaffold also greatly affects cell differentiation. The actual specialization of cells has been a mystery to scientists for many years, and to this day the process is not really understood by scientists. What we do know is that the cells are able to send signals to each other so they know where to go and what to become. A theory about how this happens is that number 1, cells receive signals by chemicals secreted by other cells, 2, making physical contact with other cells, and 3, by certain molecules in the microenvironment. The interaction of all these signals causes the cell's DNA to acquire epigenetic marks, which are marks on a cell's DNA that silence certain gene sequences and activate others so that cells can differentiate. Basically, this determines cell type. This restricts DNA expression, which causes cell differentiation, which is then passed on through cell division.
Tissue engineering in the simplest terms is to create tissues by using our own cells along with a scaffold, which is a structure where the cell grows. Look at it like making square watermelons. You put the cells into a structure so that they can grow into the shape that you would like it to. First, you will need a small piece of the original tissue, in this case a bladder, and tease the two different cells. We grow these cells outside the body for 4 weeks into large quantities of muscle cells and specialized bladder cells. Then we get our scaffold, which should be in the shape of our bladder and should also be porous and biodegradable. A good example of this will be polylactic acid, as it degrades into lactic acid, which is a common chemical that can easily be removed. Then we would inject our muscle cells into the exterior layer of the scaffold. And the bladder cells into the interior layer of the scaffold. To cultivate the tissue properly, there are many growth factors that must be considered. These will be the nutrients we have added along with the cell, oxygen, pH, humidity, temperature, and osmotic pressure maintenance. To test tissue engineering in action, scientists have accomplished something fascinating. They were able to make a human ear on the back of this mouse by creating a scaffold made of biorubber, which allows the cells to live on it, seed the cells into the scaffold, let it grow inside an incubator so it can cover the scaffold, and then finally implant it into the mouse. These scientists have incubated and grown perfect cartilage in the shape of an ear on the back of this mouse, which is completely connected to the blood vessels, making it just like a native ear. Another group of scientists from the University of Minnesota Center for Cardiovascular Repair were able to make an artificial beating heart. They used a different method to create a scaffold known as whole organ decellularization. This is when all the cells of an organ is removed so that only the extracellular matrix is left behind, sort of like the bare wooden frame of a building. These scientists insert a solution into the heart that they retrieve from a rat, which drains the cell of the heart over several hours. After it is completely drained, a new patch of cells is seeded into this scaffold, and after about a week, the heart begins to pump.
Today's the big day of the surgery. Let's see how it goes.
Oh, why, hello, Miss Lou.
Good morning, Doc.
Wow, you're in a great mood considering your condition. You've got a dying heart, a deteriorating brain, and you're in desperate need of a crucial blood vessel.
Yes, I am, because today's the day everything's going to change.
Oh, love such optimism. Now, if you'll just sign here, we can begin the transplants right away.
All right, great. Let's get this thing on the road.
Oh, well,
Just had my surgery.
Oh, hello, Lucy. How do you feel?
A bit woozy, but...
Oh, right. That's normal. Don't worry. We put a couple toxins into your immune system. Nothing big, just so, you know, your body doesn't reject the organs.
It's for my own good, right?
Yes, of course. We wouldn't do anything that's not for your own good.
But wait, didn't you take my own stem cells from my bone marrow to construct the organ?
Yes, good job. We did. But we use that only for the blood vessels that you needed.
Wait, only for my blood vessels? Are the organs from donors? How sweet of them.
Yep. They're very sweet.
What's wrong, Doc? You seem kind of hesitant.
Yeah, well, the donors weren't exactly willfully giving the organs to you.
You killed someone and took their organs?
No, not like that. Well, I guess, it's less of a someone, more of a something, if that really matters.
Just tell me what you did to me.
Okay, here's the catch. So, our technology is great. We can make things like blood vessels and tissues and even regrow skin for some people. But the problem is we're not ready to make our own hearts and brains, and they're just so complex. But we have been thinking of some alternatives in the lab, and we decided to toss them out on you.
You're experimenting on me.
Oh yeah, don't worry, you signed the forms, everything's good to go.
No, I didn't.
Oh, right. You also might not remember that because you were under anesthesia, but that's okay. Don't worry, it's all good. You have the pig's heart and it's working fine. Look at you, live. And you've got a rat's brain, which we also grew in the lab.
You gave me a rat brain?
Oh, don't worry, it was only a little bit bigger than your own.
Oh.
You're a test tube baby, test tube baby. Mommy, Meruba keeps saying I was born out of a test tube.
That's funny, children. Test tube babies. What is this, 2013? Your father and I have a very interesting history. Let me tell you about how I met your fetus.
Whenever I'm alone with you, you make me feel like I am home again. Whenever I'm alone with you, you make me feel like I am whole again.
That, kids, is how I met your fetus.
Research has been progressing at a rapid pace, and soon, widespread use of bioengineered organs could become a reality. But with the benefits come the consequences, and we must keep in mind not only the medical but also the ethical implications of this marvelous new technology. That's it for this episode of Lucy, Lou, and the Science Crew. Thanks for watching.